Well, hi guys, we're going to have a look at quadratic functions in this session, and a fascinating area it is too. So let's get underway. What is a quadratic? Well, it's a polynomial of degree 2, okay, and we dealt with polynomials last time. So yes, it's a polynomial of degree 2. That's the general form, y equals ax squared plus bx plus c, and you can see that the highest power of x is 2, so therefore that's a degree of 2. That's a polynomial of degree 2. Okay, now let's summarize what we know about quadratics. The general form of a quadratic is y equals ax squared plus bx plus c, as you know. When sketching, if the a coefficient is greater than 0, then we have a right way up, if you like, quadratic, which has a minimum here at the vertex, yes? And if a is less than 0, we have an upside down quadratic which has a maximum at the vertex. Now, c is the value of the y-intercept. In other words, when x is 0, that'll be 0 plus 0 plus c. So that's what gets you the y-intercept, okay? Now this is an important one here, which not a lot of people seem to take a lot of notice of. X equals minus b over 2a is the equation of the axis of symmetry, and minus b over 2a is the x value for the minimum or maximum point, the vertex. Now that's a pretty good little tool to have in your mathematical toolkit. Okay, just remember it. Minus b over 2a is the central part, the axis of symmetry, and the x value which has the vertex as the y value. Okay, so that's, just keep in mind that one. For the x-intercepts, we solve where y equals 0. So ax squared plus bx plus c equals 0. You know that, don't you? And this is the next thing we're going to do. So we're going to look at ways of solving quadratic equations. Okay, so point 1 was the general form. Point 2 was about sketching them. Point 3 is about ways to solve them. Okay, so you can factorize if you think you've got whole number factors, in which you, in this case, you do. So you basically, that's an easy one to do, and therefore using the null factor law, you can say that x plus 4 equals 0 or x minus 3 equals 0. Therefore, x equals minus 4 or x equals plus 3. Yes, sirree, x equals 3. Now, completing the square is the second way to do is to solve these equations. If you don't think you've got whole number factors, then you can use the completing of the square, as you're aware. So with this particular one, we have to take the 2 outside the bracket, right? Now, we've got this inside the bracket, and we're going to complete the square. So we divide. What am I talking about there? Divide both sides. Oh, yes, divide both sides by 2 just to get rid of this 2. That's before we complete the square, and we get that thing there. Now we're going to complete this little square, this square here. This is the key to it, this thing here. So basically, you take as long as the coefficient of the x term is a 1, which it is now, we're going to basically say this is the middle term. We're going to halve that and then square it. So half of 2 is 1, 1 squared is 1, and we generate that term because we want that plus 1 in order to enable us to complete this square as x plus some linear number, like in brackets all squared, yeah? So plus 1 minus 1 does not change the value of the left-hand side of the equation, so that's all right. We're going to harvest that 1 there in this quadratic trinomial, which will now be a perfect square, and this will now join this guy as the rest of the stuff. Like that. Okay? So, what have we got now? We've got a difference of 2 squares, as you can see. That 9 over 2 is actually 3 over root 2 all squared. So, yes, that gets us that expression, that equation there, and we can turn that into a difference of 2 squares like that. And then using the null factor law, we can say that. Can't we? Yes, and therefore x equals that amazing looking result. Yeah, okay, so that's completing the square. Now the third way that you can solve quadratic equations, what was the first way? Straight factorising, whole number factors. Second way, completing the square. Third way, which is actually a version of completing the square, is the quadratic solution. Okay, the quadratic solution is simply a formula arrived at by completing the square on the equation ax squared plus bx plus c equals naught. So if you were to use the quadratic solution there, yes, we've got it in that form now, okay, and then that's the quadratic solution. That is it. So you just plug and play now, and you substitute a as 2, b as 4, c as minus 7, and what do we get? We get that. And after a little bit of a simplification throughout the nation, wow, what's 56 plus 16? 56, 66, 72, right? 72. Oh, that's 2 36s. That's got to be 6 root 2. Yes, I think that's right. Yes, it is. Now we can cancel 2 out on the top and the bottom, and we're going to get that, aren't we? We are. Indeed we are. That looks like our answer. There you go. Okay, same as we got before. Oh, was it? Oh, it was. How marvellous. Yes, this one here is the same as what we got up there by completing the square, as you're aware. But it's not much of a surprise because really they're both the same kind of formula, really. So, all right, press onward, ever onward. Now, the fourth item we're going to consider in our quadratics is use of the discriminant. It's a very, very vitally important area to consider. So, for f of x equals ax squared plus bx plus c, now, the discriminant is the bit, you know that general solution. Wait a minute, I better go back and show you the general solution. That. Now, you see this this thing here. See that thing in the square root sign there, right? That is the discriminant. Now, that tells you a lot about how many solutions you get for a quadratic, because as you know, you can have none or 1 or 2 solutions for a quadratic, depending on how it cuts or doesn't cut the x-axis, right? So that thing there, that's called the discriminant, right? Now, let's go over the page again, and where were we? We were there, yes? Now, if the b squared minus 4ac is greater than naught, that thing under the square root sign, then the graph is going to have 2 solutions, two x-axis intercepts, right? Var she be. See the graph there? That's an example, right? Now, if b squared minus 4ac equals naught, then the graph of f of x has 1 x-axis intercept, and there's an example, you see? These quadratics are interesting little beasties, aren't they? Now, the other thing is, the shocking revelation is that if b squared minus 4ac is less than naught, you can't have the square root of something less than naught. It doesn't work. So therefore, we will have no x-axis intercepts, no solutions, and there's an example of that. All right? Now, here's an example for us to do. This is, we have to sketch this graph. It's an upside down quadratic, isn't it? Doesn't look too friendly either. I think we might have to get some quadratic solution or something completing the square happening here to work this out. It is an upside down quadratic, yes, so it's that kind. So the y-intercept we automatically know is the c value of ax squared plus bx plus c. So in this case c is minus 11, so the y-intercept is minus 11. Okay, that was pretty easy. The rest of it might not be quite so easy. Yes, that gives us an intercept of 0 and minus 11 y-intercept. Now, let's have a look at the discriminant and see how many solutions we're expecting, guys. Now we've got this newfound power up here in point 4 above at the top of the screen. So what would we get? What's b? What's b? Come on. b is minus 12, isn't it? A is minus 3 and c is minus 11. So let's go for that. Okay, what does it come to? Oh. It looks like it's going to be positive, so it looks like it's going to be 12. Yes. So we're expecting 2 solutions to this. So that's a little bit of good, useful information. Yes, it's greater than 0, so we're expecting 2 solutions. Now we'll go for the x-intercepts now. We just have to solve for f of x equals 0, and there at Larashi B. I think I'm going to use there. The quadratic solution is the best way out. That's the way to go. It's pretty ghastly looking, isn't it? A bit of simplification throughout the nation should fix it up. Ah, there we go. Oh, that's very nice, isn't it? So it looks like, yeah, because 12 is 2 root 3, because 12 being 4 times 3, and the square root of 4 is 2, we get that expression there. It looks like we can cancel through by 2, and we get, right, minus 2 plus or minus root 3 over 3. They are the x-intercepts, guys, okay? And of course, the y values at those x-intercepts will be 0. Right, and for graphing purposes, you need to work them out on a calculator, get an approximate, so that you get the graph looking right, the proportions right, and so on. Yes, so I've just worked those out on the calculator for you. That's the only reason I've worked that out, though, just to get the graph looking correct. Yeah. All right. So the vertex. Now the x value is halfway between the x-intercepts. So there it is. There it is. So what will that be? Looks like that's what it'll be. And that's going to be 12 over minus 6. Looks like minus 2. For me and you. So that's the vertex, right? That's the x value of the vertex. Oh, goodness gracious me! Look at that. I've done a little CAS effort on this for you. So there it goes. Look, there's one of the x-intercepts there. There's the other x-intercept there, and there's the x value of the vertex, and there's the y-intercept, and it's looking mighty fine to me. What do you think? Upside down, everything's looking terrific. Yeah, there's the axis of symmetry, which occurs where x equals 2. Phew! I'm feeling very poetic tonight. Right, what about turning point form of quadratics? Yes, okay, now this is an extremely important area. This is when you take a quadratic and you complete the square. It tells you, when you have completed the square, and it's in what you call turning point form, it tells you where the turning point or the vertex of the graph is. So, yes, by completing the square, any quadratic can be written in that form. Okay, that's there is called turning point form after you've completed the square. Now, yes, it can be used to gather useful information about the turning point or vertex of a quadratic and how it compares to y equals x squared, the original base model function. Okay, so here's an example for us to go by here. We've got example, express the function f of x equals 2x squared minus 4x minus 7 in turning point form, and describe the transformations required to change y equals x squared into f of x. Use this information to help sketch f of x. Alright, very good. This is actually a transformations question, ladies and gentlemen. So I'll show you, because we're going to complete the square on this thing here and get it into turning point form, and then I'll show you what you've got to do and how it works. There's our function. We're going to complete the square. Okay, put it in brackets so that you've got the 2 outside, and you complete the square on what's inside, right? Half of 2 is 1. 1 squared is 1, so there you go. Add 1, subtract 1, so you haven't changed the thing at all. It still has the same value. Then you get this minus 1 out of the brackets because you don't want it. You want that one there. This is the quadratic trinomial you do want, which is the perfect square. Yes? So there. Sorry. So, right. Now don't forget to multiply by 2, right? 2 out here. 2 times minus 1 is minus 2. So that gets you a minus 9 of all that stuff. So it's going to be 2, open bracket, x minus 1 all squared minus 9, right? Now, this is the amazing thing. So if the original function was y equals x squared, then the transformed function is that thing there, right? I'll put the dashes in, see the dashes? To show that that's the transformed model. Right, now we're going to put them in equivalent form, and I'll put some labels on them. So that gets you y dash plus 9 over 2 equals x dash minus 1 all squared, so that's good, so that the 9's belonging to the y and so is the 2, and this minus 1 belongs to the x dashed, yeah? Alright, now, equating like terms, we can say that, and we can say that. Yes, now, what are we trying to do? We're trying to work out the transformation steps here, alright? So that means we're going to make x dashed and y dashed the subject because it's a kind of a backwards thing. We've got the original function, the final function, and we want to work out the steps. Alright? So that's y dashed, that's x dashed, and we can just read it off now. We can just read it off because we have the key to everything. That is the key to everything. Absolutely everything in terms of these things. Anyway, transformations. Now, to get from y to y dash, just read it off, guys. We've got to multiply y by 2 and subtract 9. So that means we're dilating by a factor of 2 from the x-axis and we're moving 9 units down. Okay, there we go. Terrific. Now, what do we got to do with x dashed? Well, we've just got to translate one unit to the right, don't we? That's it, guys, that's it. So, there she be, the original, and there she be, the new one, right? Now, you might think, Wolfman, have you gone stark raving mad? Why are you doing all this? Well, it said describe the transformations required to change y equals x squared into f of x. Yes, I hear you saying, but look, you know, once you've put it into turning point form, you can just read it off, can't you? Well, yes, you can, but I'm just showing you the long way round so that, you know, it's a little revision lesson in transformations. Turning point form, this x minus h squared plus k, h comma k coordinates is the location of the vertex. Yes, I know. I know that, okay? But I'm just doing it around this way so we won't make a mistake, and we're also getting this 2 thing here into the picture as well. Alright? So, now I haven't gone stark raving mad, I'm just showing you in really detailed, simple form how you can do this using transformations. Now, over the... oh, yes, that's good. And over the page, what do we got? So we got y equals 2x squared minus 4x minus 7. General shape is that. Turning point is 1 and minus 9, because that's what we had as I showed you on the previous screen. It was 2 times open bracket x minus 1 all squared, close bracket, minus 9, right? So the 1 is the h and the k is the minus 9 in terms of turning point form, which is a open bracket x minus h close bracket all squared plus k, yep? Okay, now the y-intercept is minus 7, we know that because we're looking up here, and that's the c term of the ax squared plus bx plus c, and yes, that gets you that. I think that's just about everything. Oh no, we need the x-intercepts, that's right. We do, indeed we do. So we've got to solve that thing for 0, or we could do it, oh yes, we could do it that way. That'd be nice, wouldn't it? So therefore, x minus 1 all squared equals 9 over 2. Then just take the square root of both sides. We could do that, couldn't we? Excellent. So x minus 1 equals that, and we just add 1 to both sides, and we've got our x coordinates. Yes, we have, and the y value of those, of course, is 0 because they're x-intercepts. Yes, I did that just to show you, just to get it right for graphing purposes, okay? Which you do need to do, because it's got to be looking okay. So there they are. Oh, whoa, look at that. Wow, it's beautiful. It's a beautiful piece of work. So the vertex occurs where x equals 1, yes, and that's the vertex occurs there, and that was 1 and minus 9, wasn't it? That was our y-intercept, that's one x-intercept, that's the other x-intercept. It's a beautiful piece of work, doesn't it? Isn't it? Yep, turning point there. And that's it. That's it. We're finished. So, did you get something out of that? Quadratics are very, very interesting little beasties. There's quite a bit to them. And in the next video, we're going to look at going the other way, looking at the graph of the quadratic and then working out what its equation is. And this is something that many students find very difficult, but we'll make it nice and easy for you. So, all the best, and we'll see you next time. Bye for now.